Can you hear me okay?
Yes,
Yes.
good morning.
Yeah, good.
Good morning.
Good morning. Can you see the screen?
Yes.
Very good. All right, so let's see, we're gonna wait another 10 seconds and then we'll begin. And all righty, let's start. So what we've done is I've released a copy of the midterm for you to look at. We've got a homework that's due end of day Thursday, this coming Thursday. We've got a lab, which is going to be on Wednesday. And since we've got a pending homework, I think that's probably our first order of agenda. So why don't we take a moment and take a look at this homework 7. So we started covering it in our last exciting microcontrollers class. Yes, was there a question? No. So then I thought what I would do is see if we could cover the rest of this homework 7. And what I'll do, I think, is I'll just kind of go through the numbers, and if you see something that you'd like me to cover, you'll tell me. So I think we did question 1 last time. And if you want me to cover it again, you'll just say, oh, can we please do question 1? And we'll do it.
Let's do it.
Oh, you want to do it again? Oh,
Sorry,
sure.
I just joined and I kind of.
Yeah, I think we did it last time, but we can do it again. So Nyquist theorem tells us that if we have a sampling rate, I'll make up a number of 100 samples per second, then our maximum frequency that we can do a reconstruction at is going to be half of that, so 50 cycles per second. So this is a big problem when you have a very constrained channel. So for example, I'll give you a good example. Here's a good example. Real example. I have I set up a Bluetooth communication port earlier, and the communication port goes at 9600 baud. 9600 baud. Now, if you have the A to D converter feeding a 9600 baud communication channel at maximum speed and 8 bits per sample, or use round numbers, let's say 10 bits, right? Then the most you're going to get is perhaps 960 samples per second. So if you have 960, right, this is your 9600 baud channel, and you divide that by 2, then what that gives you is a maximum frequency that you can reconstruct of 480 hertz. That's 960 divided by 2. And so 480 hertz is not enough for voice, right? Voice needs like 10 times that frequency bandwidth. It needs like 4 kilohertz of bandwidth just for the voice. So you would expect to have 8 kilohertz of sampling. So if you wanted to have 8,000 samples per second, and you figured you had 10 bits per sample, then you'd need something like 80 kilobaud, right? You need, well, perhaps 10 times the bandwidth of 9600. So this is Nyquist comes in, and basically we saw this in our last exciting lab, where we tried to reconstruct a sine wave with different sample rates using our prescaler. And what we found out, even though we were just taking an input and running it straight to the output, while the DAC was fast, the A to D converter was not, right? The A to D converter, not only did it have a prescaler on the system clock, but it also required 13 cycles just to be able to settle. And we cranked it, right? We went to like a 1 megahertz clock, and then we said, oh, we've got 76 kilobits per second sample rate, but we divided it amongst 2 different converters. So basically, we took 80 kilobits per second, or 80 samples per second, and divided it by 4 to give us our maximum sample frequency. And then, we went even lower by using higher prescalers. We went to a prescaler of 128 or something like this. And then we said, oh, look at this. It looks like crap. It sounds like crap. And we saw it on the scope. So that's Nyquist. And I was trying to drill it into you guys so that you would remember it beyond, the length of this course, right? This is not one of those learn, forget things. This is a fundamental limitation, which you will encounter throughout your adult professional careers. So if I have a sine wave and sample it at twice the frequency, will I be able to see the sine wave? And the answer is no. And why is that? Well, at exactly twice the frequency, what you're going to see is the just the peaks or just the troughs or just the cross sections. If you're sampling it at exactly twice the frequency, that's exactly Nyquist. You're just going to see a flat line or square waves. You're not going to see a sine wave. And when you get close to Nyquist, you'll see that reconstruction degrades rapidly. So you're not going to see a sine wave when you sample it exactly twice the frequency. You're just going to see square waves, basically, or flat lines. And so that's a problem. Does everybody kind of understand why that's true? All right.
Yeah,
Let's move.
yeah, no, it's clear.
Okay. So then comes question 2. You want me to cover that one too? Or we can move on. Question 3. Here comes quantization. Quantization, I guess maybe people understand it intuitively. You have continuous things that vary from 0 to 1, and you say, well, I've only got 1 bit. Where are we going to break even? And you could say, well, if it's below a half, it's a 0. If it's above a half, it's a 1. That's quantization right there. And then you say, well, what's my, we'll say my noise. And the answer is, well, it could be like up to 50% of your total signal, right? Because you just took a signal that goes from 0 to 1 and you said, well, it's either going to be 0 or it's going to be 1 and that's it. Because you're, I don't know, computer engineering student, it has to be 0 or 1. True or false? Yes or no? On or off? So, what happens with quantization is it's the first step in sampling. First we sample, then we quantize, and then if we digitize anything, we have to go through a process of quantization because the total number of bits that we use to represent a sample is finite. And because of that, 2 to the number of bits is equal to the number of quantization levels. So whether it's images or sounds or color ranges, whatever you like, you're subject to quantization. I'll give you an example. In color ranges, you're looking at a full color monitor, perhaps 32 bits per pixel, 8 bits in an overlay plane, 8 bits for red, 8 bits for blue, 8 bits for green. And so as a result, you have 24 bits for red, green, and blue. That's 2 to the 24, which is 16 million. So there are a lot of colors. There's 16 million colors, but there's a finite number of them. A finite number of them. So let's take a look at this power spectral density. So spectra. Spectra refers to the content, the harmonic content of a waveform. So whenever we listen to some sound, it's a one-dimensional function of time, right? It's a pressure wave that's transduced in our ear into an electrical impulse that goes into the auditory nerves. So this one-dimensional function of time actually could be a very complex waveform made up of many, many different sine waves of different phase and different amplitude. And when you describe their phase and amplitude and frequency, then what you have is the spectra of the input signal. And so what happens with the power spectra is you take what is essentially a complex function. And so if you think about like, well, how do I represent some sine and cosine thing? And the answer is you use a phasor, right? So you say something like e to the I theta is equal to r cosine theta plus r I sine theta. So that's what they call Euler's approximation, which you've heard of.
Yeah.
This is not news to you guys. And so what you do if you want to turn that into a power is you take the magnitude of r e to the I theta, which is just going to be the r part, and that is going to be a magnitude at different frequencies. And so what you're going to do is you're going to say that the spectrum of a real valued process is an even function of frequency. What that means is that when you find the centroid at DC equal to 0 hertz, you're going to have symmetry about the power spectral density. So to show that, I guess what you could do is you could say spectra of a waveform, and maybe they'll give us a picture. I should have a picture in there. So here is, let's see if we can find one. They don't give you one. They should do.
Oh, there it is. The more spectrum analysis one, the black one.
Yeah. So here is, on the left, they show you the fundamental and some harmonics. These are second, third, fourth, and fifth, and sixth harmonics. They would be mirrored on the other side for real valued functions. So over in here, you're just seeing the right-hand side. You're not seeing the left-hand side. The left-hand side would be out of phase from the right-hand side. And so we would see these two things as symmetric about this left-hand corner over in here if we saw a real valued function and looked at its spectra. Let's see if we can see some more. I think I haven't done this properly. Let's just do symmetric spectra waveform. Symmetric, how about symmetric spectra? It should just show us a symmetric spectra, right? Here it is. So that's symmetric about the centroid right in through here. And you can see there's a mirror going on between the left and the right side. Let's see if there's any more examples here which we can find. Real valued functions are always symmetric. And that is what is meant when you look at this here, where it says omega. That's your frequency in radians per second. And so having it equal to minus omega means you've got an even function. And you can see an even function, right? What would be an example of an even function? Anybody know? Basic transcendental function that you probably studied in junior high school or something?
Wouldn't it have a gradient?
It doesn't matter if it's radians or degrees.
No, gradient. The function would have a gradient.
No, it has nothing to do with gradients.
Okay.
As far as I know. Yeah, an even function would be an example. An example of an even function would be, anybody know? About cosine, right? So the cosine of 30 degrees is equal to the cosine of minus 30 degrees. What would be an example of an odd function?
I guess sine.
Sine, sure, sine. So for example, if sine of 15 degrees is a quarter, then sine of minus 15 degrees is going to be minus a quarter. If sine of 30 degrees is equal to a half, then sine of minus 30 degrees is equal to minus 1/2. And if the sine of, I don't know, make up a number, 50 degrees is equal to 3/4, then the sine of minus 50 degrees is going to be minus 3/4. And that's actually approximately true. It's good to know a few functions, a few values from the sine table, quarter, half, 3/4, because that lets you approximate magnitudes, right? So let's assume you're landing. I'm landing on runway 24. That means compass heading 240 degrees. And somebody says, oh, here comes the wind. You say, oh, okay, what magnitude? That's a 16 knot wind. You say, uh-oh, my maximum crosswind is 17 knots for my little Piper Cherokee 2 single engine airplane. Plus I have a personal limit because I'm not very good as a pilot. So I better be careful about crosswinds. So you say, I wonder how big the crosswind is. You'd say, what direction is it coming from? So they say, well, it's coming from, I don't know, you're going to be 290. So 16 knots at 290 is actually 50 degrees off of runway 24, which is 240. You say, oh, look, the sign of 50 degrees, it's 3/4. And 3/4 of 16 is 16 on 4, which is 4, and 4 times 3 is 12. So you say, there's a 12-knot crosswind. And now you've used, a real example, right? This is a real example. They'll give you on your pilot's test if you ever want to go fly an airplane. So that's a, trig in action. And that's why it's good to know these things so you can figure them out in your head, actually. So that's question 5. Let's see. Now we're getting into it. Now comes the question about. Remember we talked about quantization noise. Here we go. What is the quantization value if you have a signal coming in from 0 to 5 volts? That's typical Arduino range, and you got a 10-bit ADD converter, 10 bits. So that's 2 to the 1024. So what that tells me is I'm going to have an error equal to the least significant bit. So 5 volts, right, divided by 1024. Learn to use the calculator. 1024 is a number which is equal to 0.004. So that's like 4 millivolts. Now, if I take that voltage and figure out what the ratio of the signal power is over the noise power, right? What I do is I take the signal, which is 5, and I divide it by 0.0004, and I get like a number which is 12,500. And I can square it, and that'll give me an even bigger number. I don't have a square function in this calculator. This is a really stupid calculator. So let's see. We'll square it first. No, we won't square it first. So you get 12,500 times 12,500 and gives me a number of hundreds, thousands, 156 million. So that's big, 156 million. But what I really wanted to know was how much the signal to noise ratio is in decibels, because I don't like dealing with these large numbers. So to reduce the big numbers into small numbers, what do? I take the log, and then I multiply it by 10, because decibels means 10 bells. Bells is named after Alexander Graham Bell, oddly enough. We still name things after him. And in fact, if what you did was you used the laws of logarithms, you could take the ratio of the amplitudes and just take the 10 and multiply it by 2. Take the exponent, multiply by what's before the log, because the log of e to the a is equal to a times the log of e. So what you want to do is you'll take 2, multiply it by 10. That'll be 20 log times the signal divided by the noise. And so what you'll do is you'll take, I guess it would be the log of, let's just use simple numbers, 5,000, and multiply that by 20. What does that give you? 73.9 dB. So that's about 6 dB per octave, per bit. You can do the same thing with 8 bits. Let's do it with 8 bits. So we'll have, let's see now, I guess that would be the log of 256. That's for a 1 volt signal. Multiplied by 20. And what does that give me? 48? Yeah, that's about right. So that's assuming we have a 1 volt range. And so that's a 10, it would actually be 20 times the log to the base 10 of n to the 2, which would really be 40 times the log to the base 10 of n. That's interesting. So let's try that. 40 times log to the base 2 of n, where n is equal to 8, gives me 36 dB. So it's off by a little bit. I wonder why. 256, 2 to the 8. Oh, it was 2 to the 8, right? So I had, it would have been 20 times 8 times the log of 2, which would be 48. Yeah, I'm doing logs in my head. So that's an interesting idea, right? Because here's what happens. I'll show you real quick. This is cool, actually, right? What's the log of 2 to the n? Right? Well, that's going to be equal to n times the log of 2, right? And so now what I can say is that if I want to know how many dB of signal to noise ratio I have with precision, I can say it's 20 times the total number of bits times the log to the base 10 of 2. And so that's going to be equal to 20 times 8 bits times log of 2. And that should give me a number which is equal to 48 dB. And that's how you do that. What do you think of that one? Good, right? So all you have to do is take 20 to, or you could say it's about 6 dB per bit, which if you've got 8 bits, 6 times 8 is 48, and that works out good too. 6 dB per bit. And you could say, you know, how did I get that? Well, take the log of 2 and multiply by 20, and you get 6.02. So log, if you do this, 20 times log of 2 is equal to 6.02, and that's why you get 6 dB per bit when you're doing sampling. Does that sort of make sense to people? It's kind of based on the notion of the laws of logarithms. So you have to know something like the log of a to the b is equal to b times the log of a. You know, if you know basic rules like this, then the rest of it just kind of falls right out. So that's that. So I'll give you another one. I mean, if I said I had a 10-bit A to D converter, which is true, I do, and I had 1 volt on input, what would the signal to noise ratio be? Let's change this number from 8 bits to 10 bits. Then what does this number become?
Is that just 20 log 2 to the 10?
Yeah, or you could say it's 6 dB per bit, and 6 times 10 is 60.
Yeah.
That actually makes your life easier, because then you don't have to screw around with calculators. Or actually, you do screw around with calculators. It just so happens the calculator is between your ears, which is the best calculator of all. Right? Because if you can do it in your head, then you don't need a stinking calculator, right? That's good. So then there's a separate thing here called program memory, a keyword used as a variable modifier for Arduinos, and it's used to store data in SRAM. SRAM. Well, now let's take a look. Here comes the Arduino. Dun, dun, dun. Now, everything in the dotted line is inside the chip. Okay. Everything outside the dotted line, this is where you can put your DuPont cables on. So, you know, here's A to D converter 6 and 7. You don't actually get that, but it's actually outside the chip. It just doesn't appear on the Arduino. So the data bus is in here. That's nice. Here's the CPU. That's kind of like a finite state machine. Here's your flash and your static RAM. And here's some double EEPROM. That's nice. Now it's looking to me like the flash that's kind of where your program memory is. And here's your static RAM, that's over here. So it says here, program memory is a keyword, use a variable modifier. It's used to store in static RAM. Well, no, program memory goes into flash. Static RAM is a separate thing. It's separate. It's not the same. So program memory, that's false. And you can kind of see it over in here too. I mean, if you went through the little microcontroller block diagrams, let's see. This is not the one you want. Let's just see if we got some block diagrams for. Right. So this is your Atmega 328. You can see you have analog inputs 0 through 5. This is the actual chip pinout. This is not what you see when you wire things with DuPont wires, but this is where those DuPont wires end up. And you can see the MOSI and the MISO and the serial clock. You can see digital ports, I/O ports 0 through 7. All kinds of interesting and wonderful things are going on here. And so you can see some ports. Here's another pin mapping where you can see where the analog inputs are. You can see the digital pins, and you can see pin numbers have relatively little to do with actual digital pin assignments, right? In other words, digital pin 0 is going to pin 2 of this little chip over in here. So the functional pin mappings on your Arduino don't have anything at all to do with the actual pin numbers on your chip. Those are different. And then if you look at the detailed diagram, here's the detailed diagram. Oh, no, that's what you just saw. Isn't that what you just saw? That's what you just saw. I thought we had a detailed schematic. But you should be able to see the flash is wholly separate from the static RAM. I don't know why they didn't show it here. It's just not the same. That's not good. But anyways, the answer is false. When you're using the flash to write data, it stays in flash and it's not writing to the static RAM. And besides which, you have like 32K of flash. You don't have that much static RAM. If you go to the even smaller version of the Arduino called the AT-Tiny, which is like 70 cents cheaper, you get like 512 bytes of static RAM. You really don't have much RAM. So that's that program memory. That's where the real memory is. But the problem is it'll wear out if you keep writing to it. But we'll write to it. And here is a constant variable name with program memory. And here's program memory again, now appearing first. You have your choice as to where you want to put it. It's a keyword. You can't use it as a variable. Put it anywhere you want. And is that okay? Can you do that? Is that permitted? Question 7. All those different variants on where program memory goes. And the answer is yes, it's okay. You can do that. You can put your program memory anywhere you want to. And that's good because then you can have pre-computed waveforms. You can store them in program memory, all this other stuff in case you're running out of RAM, which happens. You know, we've been using a lot of RAM lately for our waveform storage. It's better if you can store it in program memory. Let's see now. Setup, open a serial port and wait for the port to open. So here's something. Bang serial is used to wait for a serial port to connect. Do you need this? And the answer is, well, that depends. If you're on a Leonardo, the answer is yes. But if you're on Arduino, and Leonardo is a variant of Arduino. If you're on Arduino, the answer is no, you don't need that. But it does wait for the serial port to connect, and it doesn't hurt to have it in there. But if you know you're not going to use the Leonardo, don't even bother with it. Other variants of the Arduino include Arduino Micro, RF Leo, which is one that we've just devised recently, they might actually need these things to be reliable when doing communication. So if you've got an RF micro, you might need this. Or else you might, like, I don't know, start using the serial port before you have access to it.
It'll ignore my first couple print statements if I don't do something like that.
Yeah, it'll ignore the first print statement if you don't wait for the serial port to initialize and connect.
Yeah.
So this is important for those individuals who might be involved with programming Arduino variants. And that, actually, hey, look, something useful came out of the lecture. Wow. Imagine that.
Did you say first two or first few?
This is in the setup. So you might miss serial port communications entirely if you're on a Leonardo. That's important. So yeah, you wait for the serial port to connect synchronously before you do anything with the serial port. Unless you're not planning on using the serial port right away, in which case maybe it's a race condition and you can just tough it out. So here comes a longish example of using the serial port. So here comes the code. There's your setup, and we're waiting for the serial port. And then as soon as this is available, we print out this string. It says new line, string to float. And now he's looking for the number of bytes being available on input to the serial port being greater than 0. Doesn't know how many bytes there are. Could have been a while before serial.available got called, so they could have been building up. But in this case, he just grabs some input character in here, and he looks to see whether or not it's a digit or a period. And he can convert the incoming byte to a character and add it to a string. So this does string concatenation. So it takes an input string and just adds the string to the end. So this is an overloaded operator in C++. That's what that is. So that's concatenating the string with the input character, where string is an actual instance of the string class. And now here's something that comes in that's interesting. If the input character is a new line, we're going to print the value. And then we're going to take that string and convert it to a float. That's the advantage of having a first-class instance inside of a object-oriented programming environment, that the string knows how to convert itself into a float, and we can then proceed to print it. And so if you wanted to, you can take this input string and print that out. And so that's an interesting idea, because not every string that you input is going to be able to convert to a float. If I was a Java programmer, I might get an arithmetic exception at runtime, perhaps from trying to parse something that isn't really a float. So then it says you should not need the period if you only want to input ints. Now, what is up with this period thing? If it's a digit, period. Oh, right. Why would you need a period?
End of statement, I guess.
Well, I mean, what do floats look like? Right? You're inputting strings, right? 1.2. Oh, wait, this is not a digit. That's a period. But if you're only inputting ints, like 99, then I don't have 99.0, because that would make it a floating point number. So one thing I know about the strings that represent ints is they don't need point. But strings that represent floating point numbers might have a point in it, right? Because that point is a character, and I'm just doing string compares. Then what I do is when the characters come in, I want to know if they're a digit or if it's a character, like a period. Now, if somebody said, oh, and I want to be able to put in commas, right? Like 1,299.9. Well, then I'd have to look at commas and take out the commas, and I don't know if my string to float will actually handle commas properly. And in fact, if it's a number that represents money, maybe it says something like that. I mean, now we're talking about serious parsing problems, right? Because it's got a dollar sign, but only if it's US money and maybe if it's not euros or something. So, you shouldn't need a decimal point if you're only wanting to input ints. So that's a sound true. And when you're doing the parsing of numbers, you have to start thinking about stuff like that. Then the
Professor,
program
check the
memory, I
chat
mean,
here.
there's like, I don't know, 32K of program memory. It says here bootloaders, the bootloader. Maybe there's more than one. You can have a small one, The bootloader uses 4K bytes of program memory. That's probably the Arduino IDE bootloader. So if that's true, then we've only got 28K bytes left for your code and your data if you're going to put it into the program memory.
Professor, can we make sure we go over 25 through 28 before the class ends?
Yeah, but we can take part of Thursday to do that too, right?
Yeah, okay. Thank you.
So I mean, what did we do? We got up to I don't know, question 10 or something. Yeah. So that looks like a true statement. Program memory. And we're going to use program memory. And then there's this other thing called double EEPROM. And let's see if we can find a. There it is. So there's your double EEPROM right over through here. That's separate from flash, separate from static RAM, and we can store data over in there that might last for a while. And in terms of lasting for a while, I just finished reading the data sheet on the ATtiny 85, which is the variant of the Mega 328 that we normally use. It's the one that's 70 cents per chip cheaper. And they say that the data stored in the flash and the double EEPROM are guaranteed for 100 years. And I'm thinking, this is going to end up in a landfill long before then. But who knows? And so then let's see, there's a K of double EEPROM. So 32K of flash, a K of double EEPROM, and that is true for our little chip. That is true. And if you ever have a question about this, you can look at your data sheet. And then it says, there's 2K bytes of static RAM. We know there's got to be some separate storage for static RAM because there it is. So I've got, I don't know, 2K of static RAM, 32K of flash. That's cool. That's cool. And then he says my double EEPROM is only 1K. So that's kind of small, actually. And static RAM ain't so big either, although it's twice the size of the computer I had when I started. So it's pretty nice, actually. 2K bytes of static RAM. You can do a lot in there. And I don't know if I mentioned, but if you get to the ATtiny and you save 70 cents, you only get 512 bytes of static RAM. So quite a bit less. 4 times less. It's probably worth 70 cents to get 4 times more RAM, right? I don't know. Depends on how much money you really need to save. So then let's see. There's 32K bytes of flash memory. That's your program memory. That's true. And then there's this other thing in here. It says static RAM, flash, and double EEPROM are erased when you upload a new program to the Arduino. Is that true or false? Well, I guess if I'm uploading a new RAM, a new program, it goes into the flash. That's your program memory, so that gets erased. What about the static RAM? Is that also erased? And the answer is yes. It does a full reset, gets erased. Well, what about the double EEPROM? Right? I mean, there's that separate little area. Yeah, here it is, double EEPROM. Does that get erased too when I upload a new program? The answer is no. That's what makes this RAM, this read-only memory special, right? What you write here stays here until you overwrite it or erase it explicitly. So you can take, I mean, this is cool, right? You can take this thing offline, power it down, put it aside for 100 years, power it back up. The program runs out of flash, and all of the data that was stored in the double EEPROM is retained. So if you said, oh, the last time I turned this on was 100 years ago, that can be stored in the double EEPROM so that you can find that data and know that it's been 100 years since you've turned this on, and it's probably time to check your batteries or something. I don't know what happens every 100 years. Something happens. So that's false, right? This is false because double EEPROM is not erased when you upload a new program to the Arduino. And that's cool, right? That's a feature. That's intentional. So here comes another question. We're gonna actually use this program memory now. And so this string, hello from Teague Labs. This is our program memory tutorial. This string is being stored in program memory. And when you go to print out the greeting, it's printing from program memory. So you're accessing non-volatile memory, which is pretty cool. It'll disappear after you upload a new program. But on the other hand, if you power down the computer and then start it again, that string will be retained. And it's retained in program memory. So that's cool. And now we've got an array of char, not an instance of a string class. This is a big difference here right now because you have to go in with a function to determine the length of the array. So this gives you the string length. And then you can go through and check this out. You're doing a program read byte near, and now you're going to go through this so-called greeting, right? What's greeting? Greeting is a reference to the beginning of the char. Then you're going to do a little pointer arithmetic. You're going to add 1 byte in the address space, and then feed that to this thing called program read byte near. And so it's going to go and get the data from the program memory 1 byte at a time. Now it's cast to something of type char, and then it prints it out. And that's what you have to do in order to be able to gain access to the data stored in program memory. You got to use program read byte. So do I need special instructions like program read near byte or byte near to read program memory? Is that true? Do I need that? And the answer, unfortunately, is yes. That is true. So look at this ugly code and say, is it really worth it for me to use program memory? And the answer is yes. If you want to do embedded computing and you need that memory to be non-volatile, that's the place to put it. That's the place to put it. And it'll get wiped out next time you upload your code. So that's interesting. Let's look at question 16. The machine code. Machine code. What's machine code? What's that? Well, when you run a compiler, what happens is you're inputting high-level computer language like C or Java or C++, and your output is machine code. That's the operational codes plus data that are being stored in your so-called exe file under Windows, or your .so file in the shared object library of Unix, or whatever it is they're doing with hexadecimal codes being transferred over the monitor on the Arduino Uno. So if I want to see how the program looks after it's been compiled and downloaded into program memory, I can dump program memory, dump core, dump the runtime program. So what I'll do is I'll set myself up to run at high speed, 115 kilobaud, and then I'm going to go and create an interesting looking invocation. Program get far address. Get far address. What's up with that? And then it says char set. And here comes char set, and here comes some sort of I don't know, some sort of value. So that's my address, I guess. So I go in and I'm going to get a program memory from that address. Then I'm going to cast it to some sort of a pointer. And now I'll read a byte from that location in hexadecimal, because apparently it's in the hex format. And well, actually, I read the byte and I want to print it in hexadecimal format. And then I increment my pointer. So this is supposed to dump the code stored in my Arduino. You ever have a question about whether or not something like this can work? Just take it and, I don't know, see if you can copy it. I'm having a little issue copying. And then let's see if oh, there it is. See what that looks like. It says I got an error compiling for board Arduino Uno. I don't know why. Try that again.
The port.
Error. Undefined reference to, oh, my loop is missing. Interestingly enough, this didn't do anything, did it? Apparently there's nothing being stored. So this would be an invocation that you would do in the middle of your program if you wanted to print it out. So I'd have to insert it into this program I'm working on, something I'm unwilling to do right now. So let's take a look and see where we are here. Question 16. And the answer is yes. If you know, I uploaded this program and nothing else, and so it didn't have much to print, I guess. And that would have been true had I had it as a part of what was already an inserted program. Since I didn't have a program, it didn't print much, interestingly enough. What kind of data can we store in program memory? Well, here comes unsigned two-dimensional array, 11 by 10 in length, already pre-computed on its size. And it's all in hexadecimal, so this will be packed into a nice binary data structure. And I formatted it so that it has 11 rows and 10 columns. And then it says my constant unsigned blah, blah, blah has to be constant to be put into program memory. Do I need this to be constant to put it into program memory? Do I need this constant? Do you think? Or can I have dynamic memory that gets updated all the time? The answer is yeah, it has to be constant. Program memory has fundamental limitations. It's not like RAM. During runtime, you don't try and reprogram the program memory. It just takes too long. If you want to do something like that, use some double EEPROM and be careful not to do it too frequently because you can wear it out, ruin your chip. How am I doing on time? I've got time. Here. See, there's the time. That's a Java program, by the way. So let's see. Let's look at another one. Question 18. This is more program memory question. Let's see. What do we got here? Program memory is another 10 by 11. And looks like it's a constant with unsigned characters coming in as hexadecimal literals. And to read this memory, you will need something like byte equals program memory read byte, dereference the address for the RAM at that location. And the ampersand is optional. Ampersand is optional. Do I need the ampersand to dereference this? Well, my data is a pointer. So in C and C++ for that matter, the answer is yes. Ampersand is needed because it returns an address of the data, and you're trying to get the address, not the value. So you have to call by name, not by value. So program read byte expects to have the address of the data. It needs that in order to be able to read the byte at that location. So ampersand gives you an address. The asterisk will give you the value. So there's a it's kind of like a little bit of a C pointer thing. Put it that way. So now we're up to question 19. It looks like some kind of a circuit. So here's something that says touch, right? I guess you're supposed to touch it. And if you touch it, what happens? And the answer is you can discharge this capacitor by changing the resistance between these two little conductive traces. So you've created what's called a touch switch. This is a pull-up resistor. And the touch switch should change the actual voltage sensed on the analog input coming out of this this capacitor over here. It says here, the above circuit uses a human, that's a hue, that's like you, to touch the two leads, that's the touch 1 and touch 2. The role of the person is to act as a voltage divider. We need C1 and R3. Here's the capacitor, R3 is here, to debounce the circuit. And so that is true. We're trying to smooth out the noise that occurs when you touch these things. So that's essentially turning the person's skin into part of the resistor that's in circuit here. And so some of the resistance is going to go through the capacitor. Some of the voltage is going to go through the capacitor, but most of it is going to go through the person and then down to ground. And then the resistor here is going to act as a current limiting resistor. So if you have a 2 mega ohm resistance in your skin, or if it's wet, maybe even less, that's going to create a circuit between touch 1 and touch 2. You'll have another limiting resistor going down to ground. And so the total amount of current will be relatively infinitesimal. You won't feel it. And so you can make a touch switch. So that's cool. Make a touch switch. Why not? So now comes question number 20. someone said cover question 24. I think we're almost there. When you run the following code, your computer, it should say in your computer, and you are missing data in transmission, then you need some means of error correction to fix the problem. What's error correction in data transmission? What is that? What does that mean? Any ideas? I got to control error, right? I'm gonna let me put it another way. Suppose I say something like this: the time has come for all good men to come to the aid of the party. Bring your own beer for the party, right? And oh wait, I have an error in my transmission. This is air. It should say aid. Oh, so I have to go back and change it, right? That's error control. This is this time. It should say the time, right? The time. So I have to go back and change that. Okay. So if you can go back and change or repair what has been typed, that's an ARQ. ARQ, automatic retransmission request. It says, hey, this doesn't look like the right word, doesn't look right. So that's a form of backward error correction. That says go back to the transmitter and repair what you've done to change like the one or two words that got messed up. So ARQ is backward error correction, BEC. Another way to do it, if you can't go back to the transmitter, like if you have Voyager, the satellite, which is already beyond the heliosphere and it's transmitting data to the deep space network here on planet Earth, then you have what's called forward error correction. So that example is from outer space, but you could have an example that's a little bit closer to home. You could have data stored on a DVD. And then if the DVD has got like, I don't know, greasy stuff on it because of your slop from when you ate lunch, then you can't really ask it to go back and fix it. So instead, you have to have enough redundancy in the data that comes off it so that it can fix it without your having to go back. So that's forward error correction, or FEC. And you do that by building redundancy into the code words. So that's interesting. So now we know the difference between backward error correction and forward error correction. And we've now heard of automatic retransmission requests. This is important if you're trying to do digital data communications, by the way. I mean, you could, any field, electrical engineering, computer science, software engineering, computer engineering, they all have to deal with digital data communications. You guys will be doing that all the time, I imagine, with 4G and then next generation 5G networks. Got to do it. So back to the question. When you run the following code, your computer and you are missing data in transmission. You need some means of error correction to fix the problem. What do we got here? This is some piece of code. This says long, start time, end time, elapsed time. Why would I use a long for something like that? Long. Long is the time in milliseconds. And that can be like a big number. It'll probably be a time in milliseconds if it's current millis since 1970 or something like this, or since the computer was turned on or whatever. So could be a very long time. If you did this as a short, probably be out of time in no time or in short time. If you did it as an int, it would be out of time within a week or a couple of 4 days or something. So then the lines, I'm not sure, but I think that's lines of text. And it says baud rate. Now that's a pretty fast baud rate. So that's pretty, well, this is unreliable. That's why you're using it. It's interesting. So here comes the string. And now we can have the length of that line. So string is a first class. S is an instance of the string class. And here's the length of the string, just like in Java. And here's my line length, including carriage return and line feed. So I added 2 bytes for that. And now I do, here's my begin, wait for the serial port, and program starts. And now I got my start time. Oh, well, now this is not even in millis. This is in microseconds. And we know we're accurate to within plus or minus 4 microseconds. And now what we'll do is we'll print out our little serial string to our serial port. And we'll do that IND times, where IND is perhaps not defined. What is it? Oh, it's lines. So we're printing out 500 of these things. And then we figure out how long it took, end time, and we get the benchmark, so we get elapsed time. And we want to compute baud rate. And looks like baud rate is something that gets set here, right? So the baud rate was set up to be 230 kilobaud. So that gets printed. And then we print out the number of lines. And then looks like it says I want the elapsed time in microseconds, and the actual time. And this is characters per second. This is some sort of a computation that I'm using to figure out just how fast I'm transmitting. And what does this have to do with the question? When you run the following code, your computer is missing data. Well, that's because you're going too fast. So you need some means of error correction to fix the problem. Well, putting all this code aside, which was interesting code to look at, the answer is true. You're going very fast through the code, trying to benchmark just how fast you can go and finding out that you're getting errors. And one thing you can do is you can back off. Just slow it down a little bit. Go to 115 kilobits per second. You'll be much better off because it'll be reliable. Serial.end disables serial communication, allowing the transmit and receive pins to be used for general I/O. Serial.end. That is an actual serial port invocation of a method that you can use to free up the transmit and receive pins. So yes, that is true. Any questions so far? Let's look at some more of this stuff because it's interesting, right? Because you're going through and effectively learning a little bit of programming as we go. So here's something we don't see every day. F. What's up with that? F. Well, that stores this string in flash memory without you having to specifically do a flash memory write. So that's actually going to store the string in flash so that you don't have to use up any of your valuable static RAM. So if you have lots of strings you want to print, you can take the literals and store them in flash just by preceding them with a parenthesis and F. And that will free up memory in the static RAM. The static RAM is quite limited. In flash, you've got 32K. So that's cool. And any questions about this? You probably don't see this. That's really Arduino style programming right there. Because a lot of times when you do programming, you don't have flash, right? But you're on an Arduino now, so you get that. That's a feature. Let's see. Here's the splitter, right? The splitter takes two strings and splits them, or takes one string and splits it in half. So here's the splitter library test. Notice it's being stored in flash. Stored in flash. And now we're up to question 23. Question 23, which says, oh no, another long program. If you ever wonder if these programs will work, you know what you do? Take the program, copy the program, go into your little Arduino IDE, and see if it works. So this is missing something about the string library. He needs the string splitter library. And so it says I have to get it from tools, I think. Let's see. So I've created my own library, get the string splitter library from tools. So I don't have that. So this .h file doesn't work for me because I don't have the tools. If I don't have this, if I don't have the library, the .h file can't compile. So that's interesting. But if I had the library, would it work? And look at the output. String splitter library test. And what does this do? Let's see. String test. And it says string splitter puts in a pointer to splitter type of string splitter type, makes a new string splitter instance with the string test, where string test is this thing, and says I want to split along the comma. So everywhere I see a comma, and this is good if I find comma separated values, I'm going to read them in. I'm going to take every string that's separated by a comma, take every one of those strings and make an array of strings out of it. So we'll get the item count, which will be the number of items with the commas, and we'll be able to get item at index I and then print it. And so it should print something like 1, 2, 3, new line, 4, 5, 6, new line, 7, 8, 9, new line, ABC. And so here's the input. It printed out 3, but not 1, 2. Oh no, here it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the last one was ABC. So that seems to work. I mean, that splits the string, which is kind of just what we wanted to do. And so that's true. That's what it does. Looks like it's splitting the string to me. So that's cool. And this is the question somebody asked for, right? Question 24. Wanted to make sure we could do that before the end of class. It is 12:06. So yes, we can do that before class ends, which is good. Just what you wanted, right? So let's take a look and see what the question says. Some code. Outputs, blah, 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 blah. This code looks like it has a bug. Does it? How can I tell? I guess I could try and run it. Nothing wrong with trying to run it, right? So now it's printed out the program memory, looks like. Let's take a look at this code. Fill the sine wave, that's good. This is not actually writing to memory anywhere. It's doing a series of prints. But it's printing out the sine wave in hexadecimal. And then it's storing it right here on the screen. So that what I can do is I can take the output of this program and use it right in through here. In other words, take all of the sine waves, have them pre-computed and put them in program memory. And then when I compile, I should be able to get the, DD is declared twice. Let's call it DD2. Expecting a parenthesis. It's not working. What could be wrong? It doesn't work. And what's the question on this? It outputs that. This code looks like it has a bug. And the answer is true. It didn't work as advertised. There's something wrong with the code that it's generating. And so that is a problem. It has a bug, for sure. So that was the answer to question 24, the one you wanted me to do. And what did I do? I cut and pasted into my Arduino code, and my Arduino IDE compiled it so it wouldn't compile and said, yep, that's got a bug. So this is like a program that's supposed to write a program, but apparently the program it writes, it's got some kind of bug in it. By the way, what does this little line do? What's that about? Anybody recognize that percent sign? What's this percent sign do? That is working the same in C as it is in Java or C# or C++. Same operator in all those languages. You guys don't know what it does? Well, that's the mod operation. So when 8 goes into IW an even number of times, the result will be 0, in which case every 8 elements you're going to have a new line. That just neatens things up on output. So that's what that's about. So we got up to question number 26, and I thought it would make sense for us to take a quick look at the lab for next time. Since we have just a couple of minutes, I wanted to just kind of cover a little bit of information about the lab because we've got something coming up that's a little bit different. This is called the LCD display. And what it does is it gives you the ability to have an output for the Arduino. Where is the... here it is. I wanted to see a picture. So now you've got a select button, left button, up button, down button, a right button, and then there's a reset, which resets the microcontroller underneath the shield. So that is an LCD output. We're going to use that next time. You can read about it. There's documentation over in here. And what we're going to do is we're going to build a clock, essentially. And then you guys are going to modify this clock so that you can set the clock when you get into the lab. So that'll be fun. We'll have a little fun with that. The buttons all feed into analog to digital input number 0. And so they form a voltage divider. And when the voltage range changes, you get to figure out what the button is that was pressed. You can find that out over in here. If the analog to digital converter value is under 50, it was button right, otherwise up, down, left, and select. And we'll actually display those things on the LCD display. So that's kind of cool, actually. And you'll be able to cut and paste this code directly. And I'm told there's enough of these for everyone. So that's cool. Moreover, when you open up the serial port, you'll be able to transmit the date and time in the number of milliseconds since 1970. And so these are a few examples you could transmit over the serial port. And let's see, what else do we need to know? This is inputting the numbers. So parse int. We saw that from before. And that gives us the so-called PC time. And we'll be able to set the time for our little clock. So that'll work pretty good if you want to just start with a correct time or something close to the correct time. And let's see, what else do we need to know? I think that's it. I've implemented some print functions so you can output some digits. And it kind of works, but it doesn't let you set the time using just the buttons on the front panel. So we'll modify the LCD key display. So instead of it saying left and right when you press the left or right button, you're going to do things with the time that changes the actual value. And you'll use button up and button down, change the hours and or the minutes and or the seconds. And I've got this working, it's sitting on my desk now, and I'll have a little video for you guys to watch by next time. So that's what I have for you for today. And we'll finish up this homework 7 on Thursday. So thank you for your attentions. Stay safe and have a good day.